let's get today's OSC colloquium started. It's a real pleasure to introduce today's speaker, Professor Miguel Eckstein. Miguel is the Duncan and Susan Medican Professor in Mind and Machine Intelligence and a distinguished professor of psychological and brain sciences at UC Santa Barbara. In computer science and electrical and computer engineering. And he earned his bachelor's degree at UC Berkeley and his PhD at UCLA, and has held positions at Cedars-Sinai and NASA Ames. And he's a leader in vision science and AI with major contributions spanning human perception, medical imaging, and computational modeling. And his work has been recognized with numerous honors, including the Optical Society of American Young Investigator Award, and NSF Career Award, and Anne and Donald Herbert Distinguished Lectureship on Modern Statistical Modeling, and the National Academy of Sciences Chamberlain Award, and Guggenheim Fellowship. And he served as the chair of the Vision Technical Group of the Optical Society of America, chair of the Human Performance Image Perception Technology Assessment Conference of the SPIE Medical Imaging, and as a member of various National Institute of Health Studies section panels over 35 times. Miguel's research combines computational modeling, AI, behavior studies, eye tracking, medical imaging, and neuroimaging to understand how humans interpret complex visual data, for example, medical images. And his work appears in a wide range of journals, including PNAS, Nature Communications, Nature Human Behavior, Current Biology, Journal of Neuroscience, Radiology, IEEE Transactions on Medical Imaging, and CVPR, etc. So on a personal note, Miguel was my postdoc advisor, and I was about to graduate from my PhD program. Miguel reached out to me after reading my first IEEE TMI paper, and that lead me to my postdoc position at the UC Santa Barbara, where I was very fortunate to further explore vision science and the ideal observer theory under Miguel's mentorship. And actually, even before that, when I was a graduate student, I already used some models from Miguel, like the classical background. And actually later on, I find out, okay, that's Miguel's contribution, of course, and others. And even now, I'm using a classical background in both of my teaching and research. And with that, I want to present these certificates of appreciation to Miguel for the seminar.
Thank you very much. Oh, okay. Okay, we have a picture.
Okay, so with that, so let's welcome Professor Miguel Eckstein for the colloquium.
Thank you, Amin. Is it on? No, it might be. It's on from this side, so it might be. Yeah, you guys can hear me? Okay. Okay, so thanks for coming. I was trying to remember what's the last time I gave a talk here, and it was, I think, 16 or 18 years ago. Look quite different. It's like a different campus. And so thanks, Amin, for inviting me. And it's sort of an honor to come back. And it just happens to be that, and this was not planned, but it's just a coincidence that it's a day before the celebration of the life of Harry Barrett, who I was not a student of Harry, but I had a relationship with Harry through the years. He was incredibly influential in my career, as many people in this room and across the world, because of his sort of insights and vision for the field of imaging science. And I also have another connection with University of Arizona, which is my colleague Craig Abbey, who is a graduate, who is a former graduate student with Harry Barrett, and Craig and I go back together, I don't want to say it, but 20 plus years, maybe 30, I don't know, like that we've been working together. So it's just a great pleasure, and I will mention here and there, my talk is going to be about the perception of medical images. This is going to be a very brief overview of certainly a very edited version of the past, sort of picking a few examples to try to illustrate what's this field about and what is its importance, its contributions. I'll talk a little bit about the present, obviously, that's where I'm putting my work, so a little bit biased towards the work I've been doing in my lab. And don't get too much high hopes about the future. It's a single slide. But maybe that'll give us a lot of time for conversation. So again, honoring Harry here, the early years, and again, like the way Greg remembers this, the way Harry I got to know me, or I got to know Harry, is I basically chased him down the corridors with his papers, explained this to me, and I think he just found it a little bit funny that this guy with an accent, very young guy, is chasing him, and he was very kind in sharing his knowledge. And that was a proposition. This is what we looked in the early years, not, so that, yeah, I know, yeah, that was, we had a lab in Cedars-Sinai Medical Center in LA. I don't know how they let us do that with the way we looked. We looked more like a LA band or something. So that's myself, Greg Abbey right here to the right. Francois Wachou is now the director of the Institute of Radiophysics in Lausanne, Switzerland. Jay Bartroff was an undergrad that graduated from Caltech, now is a professor in either statistics or mathematics at USC. So, and we're a subset of characters from this field called the field of medical image perception. These are just a few pictures of this smallish subfield that brings together physicists, engineers, mathematicians, psychologists, and we try to catch as many radiologists, beg them to come to our meeting and informs us and tell us about how we're thinking wrong about their how to look at medical images, how to read medical images. And Elizabeth Kopinski, if some of you guys know her at Emory, is really instrumental in actually sort of pushing forward with this little small field that still pushes and is still, we have a meeting this year in Chicago. The premises of this field are, in general, at least the way I see it, the idea is that there are perceptual bottlenecks in the human eye and brain sensory processing that are shared by whom? Humans, us and radiologists. And these are relevant and constrain some of the radiological readings. Understanding how the visual system works helps us understand what are the limitations, what are the possible errors radiologists make, and so on. And the idea, the premise is, not everybody agrees with this, is studying trained observers, because it's hard to get to radiologists sometimes. But a good first step is really trained observers will advance our understanding of medical imaging science and radiology. And it provides sort of a first step. These laboratory perceptual studies can shed light on radiological decision making and also provide a first step in studying the problem before you take them to radiologists, because radiologists were not available and they're expensive and so on. Otherwise, we would not be able to advance. This field has, so the idea that perception is sort of important, that it's not just about creating the images, which is incredibly important, but everybody agrees on that. But the fact that there's also something to be gained from understanding how radiologists, how their brains, from the image, from the light, from the images that falls on the back of the retina, how their brains process that, there's some value in understanding that. That goes back quite a bit. Henry Garland is a leading radiologist back in the 50s in California at Stanford Medical School, then at University of California. And that's what he sort of reflected on, as a, thoughtful radiologist about, sort of this variability in interpretation, that even if you have the best quality images, sometimes there are these, there's unexplained human effects on diagnostic procedures. I love showing this next picture that gives you some data on this fact. This is a 2003 study by somebody called Craig Beam, now retired. He actually had about 100 film mammograms that, back in the days, okay, flew around, film mammography, flew it around the country and had 110 radiologists read these images. And sort of a little bit alarming. Here's area under the ROS curve, right? So this is 0.5 would be chance level. That's your ability to basically call, the images that have cancer correctly and also reject or the ones that are normal correctly. And so 1 would be perfect score, 0.5 is the chance. And this is sort of the variability that you would actually see across radiologists, illustrating that this is kind of large, something we need to understand. So through the years, this field they've contributed to our understanding of radiology in different ways. And and I'm going to give you some examples. So I'm going to give you very early examples of how perceptual science, understanding sort of vision and how brain sees, can be actually contribute to radiology. One of sort of a classic example. So some of you that are old enough know this, that a year after the discovery of the X-rays, Thomas Edison sort of invented this, something called a direct fluoroscope. So X-rays were visual, there were no image intensifiers. So you actually visualize these images with what were cardboard funnels, and they just had an opening at the narrow end, and then you actually had a little screen that was made out of fluorescent metal salt, and it was a very, very extremely dim image, so dim that you would actually have to, it's like entering a cinema, a theater. It's so dim that you would actually need to be there for 20 minutes to actually see something. And some of you know this, some of you might not know this, that, at the back of your retina, there's actually four photoreceptor types. Three of them are cones, which are actually what is absorbing light during daylight, but in very dim conditions, like inside the cinema. What is mediating vision is something called rods. They're at the back of your retina. And these rods actually, when you're actually in daylight, like now, they're oversaturated. They're what's called what's called bleached. And then they're sort of oversaturating the response. And for them to respond in the darkness, it actually takes about 20 minutes for them to chill out and start responding. That's why it took 20 minutes. Now, what people did, what these people figured out, is actually that you could actually use, in 1916, they discovered it because what radiologists had to do is before they actually went for one of these procedures, they would have to actually sit in the dark for 20 minutes. Because otherwise, you go and look at the direct fluoroscope, you couldn't see anything. So everybody by law radiologists required to stay in the dark for 20 minutes before they did a diagnostic. But then somebody came up with this idea of using what's called red goggles. Okay, and then there was sort of not an exact understanding of why they actually work. So you could actually, you see these guys wearing red goggles. So you go around doing your practice, red goggles, and then you would not have to be there for 20 minutes adapting. You go into the dark room, look at direct fluoroscope, take out your goggles, and you could see. Okay, and there was this other radiologist, Edward Chamberlain, in 1941, that put together all the pieces and explained to the radiology community of why that actually worked. Going back to vision work by Helmholtz and so on. And the idea there is the following. When you actually wear red goggles, what that does is it filters all the light except for the red. So the red light so you're in the daylight, but you see the world sort of reddish because the only light that's coming in is red. And then you can think, look, the peak of these rods is around green and yellow. So if you actually just have red light hitting the back of your eye, your rods are not being stimulated. So by wearing red goggles just around, your rods are not saturated or bleached. And then you come in and actually take out your red goggles and you're in dark adapted. You could possibly, those of you that still go to the theater, it would be a little bit weird, but you could, and if you're arriving late, you could always wear goggles and go in and you wouldn't have to, you would see immediately, if it's a pitch black, you would find your partner there without having to wait or bumping into other people. So anyway, it's a kind of a traditional cute example of how Chamberlain sort of put together a knowledge of vision science and sort of to try to explain a solution back in the days to this. Of course, then image intensifiers were actually invented, and then screens became bright, and all of these you have to wear red goggles. Through the years, this is a big simplification. The field of medical image perception I grouped their contributions to three different categories, and I've just listed just a few names of people that have contributed. There are many more. These are some of the people that have made great contributions, but it's a sub list. So one of the things the field of medical image perception has done is developing tools and metrics to assess diagnostic accuracy. When you're actually modifying a medical image, you're acquiring it different, you're processing it, or you're training a radiologist. How do you determine whether diagnostic accuracy has improved all of the methodology, the study design, and all the statistics that goes. And that's an incredibly serious contribution that has persisted the test of time. The second one is sort of understanding the sources of radiological errors. I mean, this subgroup trying to understand why is it that, radiologists miss, and why is it that there's variability? They read the same image and they make different decisions. And what can we do to mitigate these kinds of errors? And then, the third one is, this is what I'll be talking about, is developing a science of medical image quality, something that, Harry Barrett has, sort of led, was one of the, pioneers and leaders, and understanding the relationship between image parameters, image properties, and clinically relevant perceptual tasks. How can we connect properties of the images that we can measure to the actual clinical diagnostic task? So that's what I'm going to be talking about. And I'll give you a little bit of history of that. So this idea of relating image properties, and I will point to you, this is to another talk that was a SPI keynote in 2024 by Bob Nishikawa, that is an extended sort of talk on this topic, more, a little bit more focused on breast cancer detection. And it's online. So, check it out. It's good. So this idea of trying to relate image properties to, our ability to detect things can be traced back to the 1940s. Okay. The idea here is, at the beginning was, so here are some examples of you trying to detect something and it's in a background. And the idea is how to relate properties of the images to sort of your perceptual performance detecting it, which is ultimately what radiologists do. They detect and classify things. So the early efforts were really trying to understand the properties of the signal, like, what is it, the contrast of the signal, the area, and that led to investigate some of the critical contributions are by Albert Rose in that arena. So, and there's a great, I'm trying to remember what year it was, but there is a great paper by Art Burgess in the 2000 something called Rose Revisited that actually explains some of his model and contextualizes it on what is it that he got right and what was he missing. And then there were these folks, RCA and Dwight North, this idea, and they sort of, so a lot of these people were really the idea of a signal to noise ratio. Really, that how do you actually conceptualize that? Well, the idea that your ability to detect something is really relevant to sort of the signal and relative to the noise, and some relationship between that. But how do you measure the signal and how you measure the noise? That was up a little bit for grabs. Or do you actually measure the noise in any way? So a lot of these are really related to that. So Dwight North said, if you know the concept of a match filter, which I will talk about in a second, which is the idea is a signal to noise ratio for a detector that sort of weights the information of the signal and matches that signal, so it has a template that's what Dwight North sort of pushed forward and his work was about. And then this is a little somebody that's not really well known in USA, Vladimir Kotelnikov, who was a Russian communications engineer, and he also sort of around the time the same as Dwight North sort of also developed similar sort of theory. And I actually met this guy in the 90s. I was very, very young, and I don't know why, but I met him. So that's he's an important guy. So I gave him the time of day. Most people didn't know what he was. He showed up at a European conference. I'm like, that's Kotelnikov. He sent me all these PDFs in Russian that I could never read. Now I could probably go to Google Translate. Okay, so this is a big jump in the 50s. And again, if those of you are aficionados of all of this, I apologize if you know about it. But some of you, this might be interesting. So some of that got formalized further in the 50s. Some of it started actually in the 40s during Second World War, when people, where researchers, engineers were working on this problem of detecting, radar theory, and there were, the issue of detecting in a radar screen, sort of a ship, an enemy ship, you saw in some of those old movies, in a noisy image of of the ocean. So some of the problems were sort of similar to what then became medical imaging, and they actually were more formal in their mathematics. Some people would argue, Craig would say, argue based on some statistical theory from Wald. So obviously always based on previous work, but they did a really good job, if you read those papers, formalizing this idea of the concept of an ideal observer, the idea of actually sort of based on Bayes' theory, just making optimal decisions, optimal inference, probabilistic inferences based on the information provided and some prior information. And so this is sort of a seminal paper in 1954. Some of that work was actually classified, so it actually became declassified in the 50s, and that's a famous paper. And these are two psychologists, Wilson Tanner and John Sweats, that actually anecdote as it was told to me, they were actually in a tent building because psychology was being renovated. So they actually were next to these guys in the shared building, and they were like, "Oh, this sort of applies to how sort of the brain works. We could maybe apply that." And that's a lot of how a lot of this theory then translated to try to model perceptual science. What came later is sort of an understanding that, so here are sort of 4 different noise backgrounds with different statistical properties. So this is white noise, that's in red. So this is sort of the power spectrum. Here is cycles per millimeter, and that's white noise. This is low pass noise, and there's 3 different types of low pass noise. And the signal is always the same. So that's the amplitude spectrum of the signal in black. But you can actually change the noise properties. And what became clear to people is that the interplay, that it was not this, to understand the detectability of the signal, you really had to understand the relationship between the signal and the noise. The idea being that an optimal detector would actually weight different parts of the signal depending on the noise power spectra. So if you actually have something like this, sort of ramp noise, and the noise is like that, this part of the signal information is really relatively noise-free, so it has a lot of information. And if you have bandpass noise, you want to be using this information and that information away from the noise. So this sort of became clear in the 80s and 90s, and sort of an important challenge was really to try to understand how both you formulate an ideal observer and actually compare it on what was the ability of a human, in that case, the human being a radiologist, a model for the radiologist, what was its, the radiologist's ability to actually compensate in its ability to compensate for sort of the noise properties and actually sort of read around that noise by weighting different spatial frequencies. And that's sort of so what we see there are sort of the 80s and 90s. This is Bob Wagner and Harry, Bob Wagner and Art Burgess. Here we have Harry, and some of you know Kyle, who is a graduate also from the University of Arizona, who was a Harry's student and became really influential also for this field. And what we have here is people started getting a little bit more interested in these are all simulated backgrounds. So they wanted to just create backgrounds that were more and more because arguably that is very different from what you see in a medical image. So it started, people started becoming, well, how do we actually get backgrounds that are a little bit more similar to the anatomical backgrounds that we see in actual medical images? And how do we actually get an ideal observer, which actually becomes, as when you know all the statistics, it's sort of fairly straightforward, but as you go to more complicated backgrounds, this one is actually developed here in Arizona. This is Francois Boschut from our lab sort of did an elaboration of that, but developing the ideal observer for that was, complicated and this and that and so on. And then once people sort of figured that, there was another worry, the fact that humans, the radiologists, their visual system might not be an ideal observer. And the idea is, well, an ideal observer is important because you can use it as a benchmark to optimize image quality. But if the human can't behave as an ideal and you want a radiologist to see it, you're missing out if you don't incorporate some of the constraints of the human visual system. And that led, again in those years, to another path, which is understanding. So this was an early work by Burgess and Ishida in the 80s. The idea that the humans can't actually use all spatial frequencies. An ideal observer might be able to use something that is 32 cycles per degree, something that's varying very rapidly, but a human will not be able to use that information. And we at that time we had knowledge measurements, and that's because limits that have to do with optical limits, sampling limits, and also neural sensitivity in the visual cortex. And then into these models again, we started building more and more sort of properties of the human visual system that we were learning from physiology and psychophysics. So what we see these little funky little, these are Gaussian window sinusoids known as Gabors, and these are actually a model of the response properties of cells in primary visual cortex. Then around the 80s and 90s we started to understand. So we could actually incorporate these. Now the image was not processed by an ideal observer. The idea is we're creating a model that is actually, in a way, a subset of the information is coming through the model because it's mimicking some of the bottlenecks of the human visual system. And there I can list lots of other things that we incorporated through the years. So that was actually another big jump in the, or a push in the field to try to incorporate models that captured more components about the human visual system, and that worked quite well. And then the next step was what happened in the 1990s is for the first time we were able to digitize images. I know that sounds like what, but before that we were mostly working with computer simulated things, but we could actually now start digitizing in a large scale of digital images. So that means what you say, well, what is the effect of that? So what? Well, before these were it was hard to do sort of computation. You didn't know to quantify the statistics of these actual medical images was hard because we didn't have them digitized. I mean, so everything we do now, maybe do some analog computing, project them, but that's everything. Things were very stuck. So that was an incredible advance, and for the first time, we could actually analyze the properties of these medical images to see what are the noise power spectra of these medical images, how they agree, with what we thought it was, and also the models. Some of the models that actually I was telling you before with computer simulated images mostly were relied on these sort of closed form expressions. What we were, you could write a function for the signal. So you pick a signal that is described. You wouldn't put like a math like irregular thing. Your signals were things that you could put a function into those equations, and then you have something in the denominator that's also well behaved for the noise and so on. And this is sort of like a an assumed template or filter that the model had. So you could use these methods, but then they were in the Fourier domain, and then but suddenly now all of that, which has lots of assumptions for those of you technical, this assumes that the variance is the same at each pixel, and the covariance is also does only depend on the distance between the pixels, but it's the same across the image. Something called statistical stationarity, and then of course in medical images none of that is valid. But now, so then what models became from these close expressions, we started what's called image computable models, and that was another big, in retrospective, that was another big leap. So we went from these sort of equations for backgrounds and signals that were sort of much more restricted to actual processing images, and then the signals could actually have any shape because now it's all image computable. We're actually operating images, and then again, some of this, all of these techniques came from actually right here from University of Arizona because Harry's group was actually going from this thing to sort of a spatial domain covariance. So that all of that was actually fed into these image computable models. You could apply those directly into the images, and they were quite general. And here's one of those efforts in 1998. I mean, I had actually done some of these efforts in '94. I was happened to be at a hospital, so I was actually just fell over me. All these images were being digitized, coronary angiograms. I'm like, all right, and I was just calling people around the country. What would you do here? And they were telling me, okay, do this, that, you did that wrong. So I remember, Craig was a grad student probably here, but last year, yeah. And then Harry, and they were like faxing me stuff, fax me, did you do this, that? And I was actually, this is a paper we did. It's my only paper. Harry was actually the first author. And there was a third part was actually based on coronary angiograms that actually was using these model observers on these digitized coronary angiograms. So that was sort of fun. And then, we sort of we followed from doing a lot of work and then trying to show that you could actually using these image computable models, you can actually sort of optimize. In this case, we were trying to do optimize image compression of coronary angiograms. The idea is that you could use these computer metrics, these image computable models, as a proxy of image quality. You could use them to optimize image compression, and then you could run a study with humans and show that actually predicted that improved performance rather than to like a default JPEG parameters that were used image compression. I mean, some of you, I hope you all know about image compression, because some of my grad students say, what, image compression? What is that? JPEG, GIF, it's all the same. Because back in the days, we worried about storage. Then we worried about transmission. I don't know if you worry about these things now. Now you're just worried about LLMs. Okay, so I can't tell you how big the impact of these model observers. And here, here's the quintessential book right here, Harry Barrett and Carl Myers, Foundations Image Science. Those of you in this program cannot graduate without reading at least some of this. And it's being fundamental here, but also important to the academia industry and regulatory approval to optimize and evaluate medical image quality. Okay, I spent a lot of time there. That was the past. Okay, let's talk about the present briefly. If we run out of time, I'm good about skipping, so don't worry. Okay, interrupt with questions too, huh? I like interruptions, actually. Okay, so what's recent developments of model observers? You know it. It's neural networks. So a lot of what those model observers that I was telling you about, they're just simple linear models. But that means that they just use information about the signal shape, and they use information about the noise statistics, the covariance, and estimate sort of what is the best linear template that you can actually use. And, in the last, I don't know, well, I mean, Matt, is Matt here? Where's Matt? So I remember he has an early paper on this. Carl Myers and Bob Wagner also have an early model, and Wei Min has sort of done a lot of recent model work on using neural network model observers as to approximate the ideal observer. And the idea is that when you formulate an ideal observer in the classic way, you're restricted by a lot of assumptions you have to make that you don't always have. So these sort of data-driven neural network models allow you to approximate the ideal observer, which is always, even if you're going to use a human model observer that mimics humans, the ideal observer is always a useful tool. So, by the way, look, this is the neural network model observers through the years. You're like, oh, there's a big, we just started 2026, okay? Don't get worried. I'm sure it's going to go up further, okay? So it's going up through the years. In the last, 10 years, these kinds of models are, and they're sort of, replacing or complementing sort of our old traditional linear models. And, so there's that literature using neural network model observers to calculate the ideal observers for images that are more complicated, where you don't have mathematical expressions that describe the signal or the backgrounds, or they're just a little bit more complex. And also using neural networks as powerful, more powerful models to approximate human observers rather than that old linear model observers. And here are some examples. And I wanted to give you an intuition. Well, what does a neural network model observer that mimics humans have over an old linear model observer? What does it have? And some of you maybe, well, obviously linear models are much more limited. Neural networks are non-linear. So, and what they can do very well is that, if you have a complex image and you have an anatomy and complex things that mimic targets, like little objects or other things that mimic what you're looking for, what neural networks are good about is about learning about those representations of other things and not being fooled by them. As an example, I'll give you, this is from a recent paper we published, with a group from Penn. And here's the input. This is a phantom. So this is an input phantom image, a phantom digital breast tomosynthesis. This is a single slice. And then what you see is this is a CNN output of what are the suspicious. This is actually a image that does not have. It's a normal image that doesn't have any sort of simulated lesions in there. But this is a CNN output, and you can see a few hot spots where it thinks these might be a lesion. But look at these are outputs from our linear model observers, old ones. You can see they're fooled by everything. So these are like sort of false positives. So this is what a CNN gives you over these. If you actually try to mimic search, all these little things here will generate false positives because it just treats them as noise, and the linear model observer gets fooled by a lot of things. But the CNN model is way more powerful. And as you might imagine, radiologists are not and a trained observer will not be as fooled as these models. These models, they do something like the CNN. They're able to discount or ignore things that look like what it's like the signal it's looking for, but is not the signal. So it's just part of other anatomy. So that's one big recent development in this area. And then, and the second one, which is I'll spend sort of the rest of the time talking about, is model, sort of the challenge of model observers as we actually move towards sort of 3D medical image modalities. I will talk about mostly digital breast tomosynthesis, but this sort of applies to others. To what extent, we will see. And the idea here is, and then now this is going to be a movie that I think is going to play. So, oh no, it didn't. Okay. So as you know, this example is this is an actual digital breast tomosynthesis case, and as you, I think you're all familiar, but what digital breast tomosynthesis does, it takes multiple low-dose X-ray images of the breast from different angles, and it creates sort of a high-resolution sort of cross-sectional slices, typically sometimes 1 millimeter each. So instead of getting your traditional 2D mammogram, what you get is a sort of pseudo-volumetric 60 to 100 slices, depending on the system and everything. And the doctor is actually scrolling through this. And you say, well, why does that require new model observers? What is that? Can't we just apply the old? Okay, so let me explain. So one of the things about this is that there's a lot of data. There's 100 slices, and doctors actually take about 2 or 3 minutes. That means that unlike in a standard mammogram, you have enough time to look at everywhere. Look at everywhere. But you're not looking at everywhere here. A doctor is not, because they'll never finish. In 2-3 minutes, you can't. You make about to take 200 milliseconds to make an eye movement, 300 milliseconds. You stay at each place. So you're checking out a few places. And if you don't believe me, let's see if that works. Here we go. That's a local radiologist being tracked. And she's checking out a few places, and then going back and forth between the two views. So, and then scrolling through. These slices are correlated. That's why you can see sometimes they're getting blurred and blurred. Those are the different slices. They're highly correlated. Why is this important? Why is this fundamentally different than looking at 2D images? It's because the radiologist is not just relying on what's called foveal vision, the place they're looking at, but they're processing part of the image with what's called the visual periphery. Okay, so some of you know this, but some of you might not. So the radiologist is looking there, but then part of the image is being processed with the periphery. Now, in a mammogram, you look at everywhere, but here you just look at a few spots per image. And what we know, or you probably know about this, is that your vision at where you're looking at, that's called the fovea, is with high spatial detail. And in a way, there's a drastic reduction in the spatial detail. This is your ability to see. So this is where you're looking at, red. That's in red here. That's you can see high spatial frequencies. And as you go outwards, things that fall away from where you're looking at, you can see that there's a high reduction in the sensitivity to either high or mid frequencies. If you want to just give an example, look here. This is an example of amorphous classification group that we've put a circle. You can look at it and you can sort of see them, the little speckles there. Now look at here, and try to you can't see a damn thing. Yeah, that's what's going on. You can do a study and force a radiologist so we can actually put a little. So we give them this and say, well, look, the lesion is might appear here, and I want you to tell me whether it's there or not. And we can vary the fixation point, and they can't move their eyes. And we have an eye tracker. I think an eye tracker is a device that actually, with an infrared, light that shines in the eyes, in the eye of the observer, in the case of the radiologist, and you capture it with a camera, and we can know where they're looking at. And if they look a little bit away from where they told me, the drug is terminated. So we can force to look there, and then we can vary the distance between where the signal appears there and the fixation, and we can measure their ability to see it. And it's exactly what you see. So this is a mass. A mass is much bigger, and also has more low frequencies. So it actually survives better. You can actually see it from the corner of the eye. The microcalcification, when you look at it, it's super salient. But when you actually look a little bit away, it drops dramatically. Okay, so what are the consequences of this? The consequences of this is that if you measure it, so this is a radiologist looking at a simulated DBT, and that's where the signal is. It just appeared for a few slices. That's a microcalcification cluster, and this is the eye tracking. And what's happening is so they're looking around at a few places, and it appears at some point in the periphery. They just miss it. Okay, so what this provides is, again, sort of a vision science basis to actually say, watch out with microcalcifications, because 3D in general, what we know, is super helpful, because what it does is it removes some of the overlap of tissue. So masses are greatly detected in DBT versus masses. But something people have found is that there's more conflicting with microcalcifications. Sometimes they're actually missed. And this study that we did, both with our subjects at UC Santa Barbara, the students, and with the radiologists, we actually showed that this is actually the case, that they actually miss these small microcalcifications when they're doing the 3D search. Here's the data. So this is, again, the 3D search. Now, this is the 2D search. What we do for the 2D search, this is not mammography versus DBT. Because mammography and DBT, they differ in various ways apart from being 2D and 3D. They also, they vary in the resolution, and so there are other differences across here. We are interested in here isolating sort of this issue of 2D versus 3D. So this 2D search is created by getting the center slice of the 3D of these. So we get the slice where the microcalcification is, and we just present it by itself. And the surprising finding, these are the radiologists, as you can see, that they're actually doing counterintuitively worse in 3D than 2D. And this is explained because you just experienced it. The fact that there's the microcalcification, this doesn't happen with the masses. With the masses, they do better in 3D. For these tiny microcalcifications, they're missing them because they appear in the periphery. Now, this graph also gives you another nice bonus thing. Remember those CNN model observers that we said? When we apply a CNN model observer that supposedly mimics human to this particular comparison, it predicts that 3D is better than 2D. Okay, so here is an instance that these new CNN model observers are differing on how they actually, and the difference between 3D and 2D, respect to these model observers. We're missing something in the model observers. And then again, this finding, you can actually see it with actual images, is actually reported in this paper. So then the final challenge we have is, how do we actually modify, how do we upgrade our model observers to capture the human? What's missing in a standard CNN model observer is it actually doesn't have a fovea, and it doesn't have foveal peripheral processing. So the challenge here is, if we want to, how do we upgrade our model observers so they can actually capture sort of the foveal and peripheral processing, and then also predict sort of what we see in radiologists. And what we did is, through some years, we sort of built this model. And what this model has is, you remember we had these, channels that actually are supposed in your primary visual cortex. And what we do is we basically change these channels are changed as a function of eccentricity. So if you look somewhere, you get some spatial detail, but away from it, you lose spatial detail. This is what this is trying to model. You can see we sort of recreate that by showing that away from where the model is looking, everything is blurred out. That's just a representation. And then what we do is we have a model that actually, we can make the model follow the human fixations and try to see if we can capture the effect that we see in radiologists. Or we have an algorithm where the model is actually searching for lesions. And that's sort of, we did that, and this was a successful model, and we were able to predict, sort of this effect this model can predict this effect, the fact that 3D, obviously it has to be a search. Not only if you have an exhaustive search, if the model goes everywhere, you will not have this effect. But if it's actually just searching for about the same number of fixations as the radiologist, it will show this exactly the same effect. Now here's something we are. For those, I don't know how many ideal observer aficionados there are, but something I've been trying to work for now 7 or 8 years. And actually, Wei Min started this, and we built on his expertise. There's a lot of hard work in there. Is trying to build a model observer that actually takes optimal actions. So the model is a model that actually, so this is a model, it's a foliated model, but it's actually trying to decide optimally whether it should actually, because you have the radiologist has two decisions, right? You have a slice, and it can actually make eye movements and inspect that, or the radiologist could decide to scroll. What would be an optimal model do? How would it actually take the next action? There's some beautiful work published in Nature by Yanepnik and Geisler that provides such a model with lots of assumptions that don't work, because assumes a lot of statistical independence, and that's what Wei Min sort of worked on, trying to bring that model and make it applicable to our images. And then a recent postdoc has been working for a year, and I'll be showing you some of the first. This is the first time we're actually presenting this. So this is an optimal model looking for. So that's what the model is looking at, and it's looking for mass, and it's basically making optimal decisions. And what is it that you actually see? It's actually making few eye movements and scrolling through quite a bit. That is called, Stephen knows this, I don't know, it's called drilling. Okay, that's kind of you're drilling, and now does that make intuitive sense? Actually, yes. The math. Just think about if you could actually see really well. You're trying to detect something you can see really well across the entire periphery. That's the case of the mass. That you don't need to look around. Then you can look at one place and then just go back and forth, because you will detect it within the corner of your eye. Then you maybe make an eye movement. So this is actually very intuitive, that would be the optimal solution. And now if you actually contrast that for this 3D ideal searcher, what we call it, that it's actually now trying to search for something that is actually not detectable in the periphery. What do you think? What would you expect it to do? There's a quiz. I had to have my quiz time. Stephen, you were on the thing. What would an optimal model do for looking for microclassifications? I give bonus, in my class, I give a bonus for wrong answers. So,
So so it would be ideal for the model to do when looking for microclassifications?
Yeah. Would it,
like a single one or multiple?
You're into multiple. One.
I asked because it looks like a twinkly star pattern. If you have like multiple classifications, and
one. Just one. What do you think?
Probably scan and not drill.
There you go. There we go. He knows the answer. So there you go. Boom, 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 boom. So there you go. So so you can see that the beautiful thing about this is an emergent property of the model. And what we're trying to do is, it might explain, does it explain how radiologists, search? Is it, can we actually see dissociations? Of course, some radiologists will say we sort of search for both at the same time, which makes things more complicated. Although some radiologists recently said, no, I actually look for one and then go and do for the other. So we're confused. Different radiologists tell us different things. Okay, so I have 5 minutes, because I want to leave time to questions. I know it was a lot of information. So if you're not familiar with this field, you're like, God, you threw a lot of us to us. But, come ask me for more questions if something was obscure and you want clarifications, or if you have objections. I love those. So, I typically get them with an interruption. That makes it more exciting, but you can come after with objections. I find them also cool. Okay, so the last part is, and I'll have the future. So I have 5 minutes for all of that. So I've just told you that there is this issue, right? I talked about the model observer, but before that, I told you about this issue that these small signals, like microclassifications in these DBT images, 3D images, are often missed. And that's a problem. And then the question is, how do you mitigate? And then we gave, again, a scientific investigation of that. And what we found out that in clinical practice, they're already doing, you talk to radiologists, they don't exactly understand what they're doing, but they're already doing it in some way, and I'll tell you why. So how do we, mitigate search errors, detecting small signals in 3D? The first thing that they actually do is a lot of places, and I think it's, Colloquium calls it the C view. They present with a 3D image, they present what's called a synthetic 2D image that accompanies the thing. It's sort of, and it's, I can correct it, it's sort of some proprietary thing. We know it's nonlinear. It's not just averaging, but who knows what it is. It's some sort of nonlinear thing, and what radiologists do is they look at this 2D image first, a lot of them, and then they get sort of guides them, and then they go through the 3D search. And then, I think your intuition that what happens is that, can you see these microclassifications in the 2D image? Yeah, you can. So you can typically see them, and that tells them, okay, this is about here. So now I'm going to concentrate there. And when you do that, and we've done this, we published a paper doing this in the lab. This is not with radiologists. We published this paper in IEEE a few years ago. We can show how our version of a C view that we did. So the C view is the synthetic 2D image that accompanies the breast tomosynthesis, how it actually improves the 3D search, and it mitigates these errors. Mostly because the 2D image provides some idea to guide the eye movements, and you're not going to miss them. So that's the first method. What do you think is the second method? And this is already there. This is what is in the clinic. So they're already using it. We provide sort of a scientific explanation why this works and what is it that it's solving. Because if you talk to these people, they don't even know what it's solving. But some engineer maybe figured it out and they put it there and it works. What do you think is the second solution? It's sort of obvious. It's obvious and it's everywhere. What would be the second solution? AI. There we go. AI. Okay, very good. AI. So and this is the second paper we published, and we were showing. And the interesting is here is this. Again, this is sort of all with our trained observers, no radiologists. So if you do it, so if you actually have these are our students, trained students. And this is the ROC curve. And then, so with the CNN in 2D, there's a marginal improvement. But you can see that the calcs in 3D, AI helps quite a bit. And it's what you think it is. It's sort of like, so here's an example of a trial. So here's these are the boxes where so that's somebody's eyes. And then the little box shows up. The eye is not perfect. It has errors and so on, but it just shows up. And it actually sort of guides people's eye movements, and you're able to catch more microclassifications and reduce sort of errors. Okay, so the AI. So again, this is also there, and this paper provides sort of a scientific understanding of why it is, what's going on, how it guides eye movements, and it avoids missing sort of these microclassifications. And in a recent study, we're trying to extend this notion of AI and how it actually improves diagnostic accuracy. But we're just, right now, the paper that we've had is mostly in 2D. It's with mammals, so this is a recent paper. This is a recent paper that we were part of. This is from Johannes Chopola's group in the Netherlands. And this is a big paper where Craig and I mostly served as guiding them, the analysis, the eye movements. It shows how sort of AI can actually help. And I know you're saying, AI standalone is better than the AI. This is radiologists alone. This is radiologists with AI, and then standalone AI. Okay, but for now, the Dutch don't even consider. Craig, you might say something. They don't consider AI alone. Well, that's what we'll talk a little bit about the future. They're considering it. They're considering. Well, let's talk about it. This is the future. So, and this is sort of where the eye movements are, and it just shows you how it again. So here's with AI support. This is without AI, and you can see this is the coverage. So what happens is you can see that with AI, the radiologists are looking at more sort of specific places, reducing their times, not exploring as much because they're using AI to sort of guide. Okay, I'm a little over my time. This is my one slide about the future. This is maybe where Craig and I might have actually different opinions. So obviously AI is here. There's just no way around it. I personally, this was one of the big ones that made it a reality. This big study that came out in 2020, but there are many more. There's zillions coming out after that. So I tend to say that, I tend to think that these are the sort of three ways that at least, is it because of what patients are comfortable? Is it because of radiologists lobbying? I don't know. But I would say my prediction is this is how it's going to go as a first step. You already had human AI joint reading for many years in mammography, right? You had the cat, it sucked, right? Expert radiologists said I ignore it. And then the ones radiologists are not so good, it's like, oh, I use it. But I think obviously this is, the new generation of deep learning is making it much better. So I think that will continue and it'll be much better. Then this is the second mode, where I think, at least in my updated version, is what Netherlands was considering, sort of this idea of actually triaging the cases. So you maybe have the easy cases, just have the AI. You first have some algorithm to actually determine the difficulty of the case, and then you just send the easy cases to the AI, and then maybe the overworked radiologist focus on the more challenging cases. So that's the second one. And I think this one is definitely a very important application that I think is going to be a reality. And I think this also tells you about, so what is AI for incidental findings? And Stephen knows this, that one of the big things is that when a radiologist is looking for a given disease, if there's something there they're not looking for, they're going to miss it oftentimes, unless they're but they often miss things that they're not looking for, are unexpected, and so on. We have tons of literature on this. And that's where, and it could be sort of obvious, but they're not, they're just doing these repeated searches looking for things, and there's something there that is not their expertise. Maybe they saw it a few times. And I think AI is, there are already papers showing how AI would be really good to flag these things. And I think that is an example of what is the role of medical image perception in sort of the new era of AI, which is really trying to identify what are the weaknesses of humans and trying to and that informs us how to integrate AI to sort of complement humans and sort of mitigate some of these weaknesses, whether it's peripheral vision, like I was saying, right? The small things is the AI can tell you, hey, don't miss this because, or incidental findings, where we know humans have a bottleneck. So with that, here are the protagonists. So this is all this work is. This is a subset of the list of people that have worked on these different things, and people sort of have moved on to academia, government, or industry. So thank you very much.
Okay, thank you so much for the incredible and insightful presentation. Any questions from our general audience? Yeah, maybe yeah, please go ahead.
Radiologists be your readers for images. Is there any relationship between what you found and maybe pathologists reading tissue?
Yeah, there are some. I mean, we were just talking to Stephen and Craig knows more. I mean, I've sort of followed, but so some of the issues are similar, but some of the issues are not. I think in general, first thing, what about pathology? What about the talk is related to pathology? There are clearly perceptual issues in pathology. Are they the same? Probably not. Each modality. So I think I remember we had a conversation about if an image is very, very small, then this issue about the peripheral processing that I was talking about is less of an issue because it doesn't occupy, right now these big images are displayed like this and you're looking somewhere and this is falling way in the periphery. But if you actually have a small image, then these issues of peripheral processing, so that issue is not an issue, but there are sort of other issues but there's clearly something, you still have tons of data and you're sort of searching through tons of data. So that challenge is there. And Craig was, we were talking with Stephen about this. One of the big challenges about doing anything in perception with pathology is the pathology is the gold standard, the ground truth for everything else. So when you're using pathology, it gets a little bit trickier. But maybe you had something in mind that you thought, and you can tell us if you work with pathology images.
I work with pathologists.
Okay, so maybe afterwards, or if you have now, you can tell us what you think our challenge is. Okay, because that would be cool. That would be cool to hear.
Any more questions? Maybe I can just ask a question regarding the future or the vision to the future. So there's like AI has been developed a lot for many tasks like vision tasks, and in terms of the observers, right? So observers will be computed based on specific image statistics or a group of objects or images with specific statistic behavior, and but there is also like a generic AI that people is very interested in, right? So for example, the AI can just perform a wide range of tasks. Do you think in the future that there might be a generic AI kind of observer that can do many tasks and to aid medical image perception, or we should be paying attention or be careful about that AI techniques?
Yeah, well, there are two things there. One is the type of AI, right? So I try to make this distinction, which is sort of self-supervised sort of AI with the stuff that you see LLMs just predicting what's next, but it doesn't really have any ground. It's not supervised learning,
Right.
So that's very different from the type of things that we have,
Right.
that we try to apply here, which is supervised, which is much more task goal. And so I tend to be more comfortable for important stuff. I'm comfortable with supervised learning. I mean, the self-supervised, you all know, you go there in a LM, it thinks it's talking about it makes sense, but then you start digging like it has no idea. So there's gaps. So I would imagine a self-supervised sort of thing applied to this would also have the same limitations. So that's one thing. Now, in terms of supervised learning, what I would also, probably my intuition is I would not want a generalist AI model that can actually is able to identify the cereal at the supermarket, the tires, and also do the radiology stuff. Mostly because the domains are so different, it's hard for me to understand how figuring out whether a tire is the cereal at the supermarket will actually improve this. If there is sort of, across the natural world, I understand how training it to do different things in the real world will actually, there's sort of that cross-training will benefit different tasks. I mean, this is something that Google has been considered, sort of this narrow AI versus general AI. But for our stuff, I mean, clearly, I think we want models to understand about clinical history and all these other things. So multimodality but everything within the medical domain, anything that's relevant to our diagnostic accuracy. I don't know if you can actually bring, palpation, data and actually feed it in. I mean, all of that, which is what a radiologist and a doctor, a doctor uses, using the radiology screening, the palpation, the clinical history, all of that I think is really relevant, but I just don't see having, I don't know if even a patient would like, who's reading your thing, it's the same AI, ChatGPT is doing this and that. I think they would be more comfortable with AI that's specialized for radiology and scrutinized. Anyway, that's
have expert AI.
I think so. I think
AI for many important tasks.
Yeah.
Okay, then any more questions from our audience? Yes, please. Yeah.
This one. I was just curious how you trained your tomosynthesis visual search model, because obviously the problem with a CNN, right, it's sampling every single pixel simultaneously, but to actually get a model to learn how to search, was it kind of like a reinforcement learning model, or that sampled patches?
No,
or is this just based off human eye movements?
So you talk about maybe this one, the optimal.
That one, yeah.
So this, believe it or not, has closed form expressions because it's all So you can actually calculate sort of what is the expected performance, because you have the probability. You have to read the Niemnik and Geiser that starts that tradition. So it's not using RL. But to your question, this cannot be applied. Do you see the background? It's computer generated.
Yeah.
We're back to like the 80s, but for this. So we went back and we wanted to have solid math and a solid foundation. And now you're where we're next. We're actually now using RL methods to try to. So Waymin has a very important underside a few years ago where it was just 2D search, but he calculated using closed form expressions what is the ideal searcher in 2D images, and then he used a sort of a neural network with RL to actually train it and show they actually converged. For this, but you can do that just where you can actually calculate it with math. So that's a great paper that not everybody knows about, and that's what he did in my lab. Now what we're doing is we're trying to do the same, but now for 3D. So we're trying, but the whole thing about the RL is that you can apply it to any. You don't need, to actual medical images. So we're maybe a year away from that, maybe, if we're lucky. Everything takes longer. I don't know in your labs. My labs, everything takes longer. It takes forever, but you end up with something you like. Yeah.
Right. There's no more questions. Let's thank our speaker, Dr. Miguel Eckstein, again for this wonderful talk.